Hey guys, in this video we're going to talk about permutations and combinations. Now both permutations and combinations involve choosing a certain number of objects from a bigger collection of objects and counting the number of ways there are to do this. For permutations we care about the order in which they were chosen. For combinations we don't care about the order in which they were chosen, we just care about the result. Anyway, if that doesn't make any sense right now, don't worry, it's going to make sense pretty soon. So, first of all, though, before we get into that, I want to find out the number of ways to order these 5 marbles here. This is marble 1, marble 2, marble 3, marble 4, marble 5, right there, in case you weren't clear which marbles I was talking about. I know they're just black dots, but please use your imagination and imagine them to be marbles. Okay, so I want to know how many ways I can order these 5 marbles, how many ways I can place them in an order. Well, let's suppose that we got 5 spaces to fill. 1, 2, 3, 4, 5. Okay, so 5 spaces to fill. Let's go ahead and let's fill the first space. Well, to fill the first space, we can fill it with, say, marble 1, or we can fill it with marble 2, or we can fill it with marble 3, or we can fill it with marble 4, or we can fill it with marble 5. That's 5 choices. 5 different, I'll write it up here, that's 5 different marbles that we could put there. But supposing one's already gone, suppose just for the sake of it that we put this one there. In the next box here, we could put this marble, or we could put this marble, or we could put this marble, or we could put this marble. So that's 4 different choices, 4 different ways to order it. Actually, for each of these 5 ways, for each of these 5 choices that we had at first, once we've made one of those choices, there's 4 other marbles. So for each of the 5 choices, there are 4 choices to put the next marble down. And that gives a total of 5 times 4 choices, because for each of those 5 choices for the first marble, there are 4 choices for the second marble. And so on. Suppose that we put marble 3 there. Well, that gives us another 3 choices for the third one. So for each of those 5 times 4 choices for the first 2 marbles, that gives us a total of 3 choices. And let's suppose we stuck marble 5 there. And finally, we've got 2 different choices to go in the 4th position. We could put marble 2 there or marble 4 there. 2 different choices. So for each of those 5 times 4 times 3 choices, we have another 2. And finally, we've only got one more choice for the last one. We've only got one more choice for the last one. And this number here we call 5 factorial. 5 factorial. So there are 5 factorial different ways to arrange 5 marbles. And there's nothing special about the number 5 or marbles. In general, it is true that there are, now let me use a different color. In general, there are n factorial, which is equal to n times n minus 1 times n minus 2 times ... times 2 times 1. There are n factorial different ways to order, or another word for it is arrange. There are n factorial different ways to order or arrange n objects. So there are n factorial different ways to order or arrange n objects. So that's kind of important. Okay, what we're going to do now is the calculations for permutations and combinations. We're going to see how that works. Okay, let's go back first of all to 5 marbles, we'll say. We'll call them 5 marbles. Sorry about the drawing. 1, 2, 3, 4, and I'll draw the 5th one over here. So these are the 5 marbles. Let me color them in a bit better. Got to make them a work of art here. All right, so these are my 5 marbles. Yes, I only have 5 marbles. These are my 5 marbles. Marble 1, Marble 2, Marble 3, Marble 4, and Marble 5. Okay, so first of all, I'm going to say order doesn't matter. So right now, I'm going to choose some of the marbles. I don't care which order I choose them in. I don't care which order I choose them in. I just want to know the number of different ways to choose a certain number of marbles out of these 5. Better give them a label. So this is marble 1, marble 2, marble 3, marble 4, and marble 5. Okay, so in this case, order doesn't matter. Now, I want to find out the way to choose any one of these marbles, the number of ways to choose any one of these marbles. So number ways to choose one marble. What's the number of ways to choose one marble? Well, it's quite obviously 5. I can choose marble 1, I can choose marble 2, I can choose marble 3, I can choose marble 4, or I can choose marble 5. So what's the number of ways to choose one marble? It is 5. So nothing hard about that, actually. Okay, now I want to know the number of ways to choose 2 marbles. Number of ways to choose 2 marbles. Okay, that one might be a little bit more complicated. We need to do a bit of math here to work this one out. Okay, so I've got 5 different marbles to choose from. So I have 5 different marbles to choose from. I only want to pick 2 of them, and I don't care which order I choose them in. So here are my 2 spots to fill. Okay, here are my 2 spots to fill. Well, how many different choices are there? Well, first I could choose marble 1, or I could choose marble 2, I could choose marble 3, I could choose marble 4, or I could choose marble 5. Any one of those 5 marbles will do. So that gives me a total of 5 different choices. That gives me a total of 5 different choices. Now say I chose marble 2 to begin with. And then for each of those 5 different choices, I now have 1, 2, 3, 4. I have 4 other guys that I can choose. 4 different marbles to choose for my second choice. 4, not 5 again. So that gives me a total of 5 times 4 different ways to pick one marble and then another marble. Let's say I chose marble 3. Well, then I'm done. So 5 times 4 different ways to choose 2 marbles. But what I said at the start was order doesn't matter. Order doesn't matter. The calculation I just did, actually order does matter, because under the calculation I just did, I could have chosen marble 1 as the first choice, and then marble 2 as the second choice. Or I could have chosen marble 2 as the first choice and then marble 1 as the second choice. Both of those are counted as different choices under this calculation right here, even though under both choices I would end up with marble 1 and marble 2. I would end up with both marble 1 and marble 2 after the selection of 2 marbles was made for both of those choices. So I want them to be counted as the same choice. I don't want them to be counted as different choices. And so what I need to do is actually divide 5 times 4 by 2. I need to divide it by 2 to get rid of the double ups, to get rid of, I don't want M3 and then M4. I want it to be the same as M4 and then M3, but by just blanketly calculating 5 times 4 without dividing by 2, it's treating this one and this one as different choices. They're not the same choice under this calculation. So dividing it by 2 is going to actually, yes, it's going to count these 2 as the same choice. They're both going to be counted as one of the 10 choices. Okay, so we're nearly done. Well, I just want to make an observation here now. 5 times 4 is actually equal to 5 times 4 times 3 times 2 times 1 divided by, well, 3 times 2 times 1. The reason why we're dividing by 3 times 2 times 1 is because these cancel off. We just wanted to end up with 5 times 4, right? And that's what we've got. And since we're dividing by 2, we better divide the other side by 2. But 2 is also the same as 2 times 1. So these two things are equal. 5 times 4 divided by 2 is the same as 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 3 times 2 times 1. I'm sure nobody disagrees with me. If you don't like that, put it into the calculator and see what you get. Well, what we've got on top, 5 times 4 times 3 times 2 times 1, and I better use a different color because things are getting a bit close together there. What we've got on top is actually 5 factorial. 5 factorial. So 5 times 4 times 3 times 2 times 1 is 5 factorial. And on the bottom, this 2 times 1, well, that's equal to 2 factorial. That's equal to 2 factorial because 2 times 1 is 2 factorial. And now 3 times 2 times 1, well, that's equal to 5 minus 2 factorial, because 3 factorial is equal to 5 minus 2 factorial, right? Because 5 minus 2 is 3. And what we call this, this has got a special name. This is the number of different ways to choose 2 objects out of 5, and we write it like this. 5 choose 2. So 5 choose 2, and 5 choose 2 is equal to 5 factorial divided by 2 factorial times 5 minus 2 factorial in general. Okay, well, that's a lot of work. Let's go to a new board now, because I don't feel like rubbing that out. That was a lot of work. Okay, so can I go back to 5 marbles now? Marble 1, marble 2. I really should be more organized and draw these things beforehand before making these videos. Marble 3, marble 4. That's a horrible marble. Marble 3. No, that was marble 4, wasn't it? So marble 5. Okay, so we're done with our marbles now. Marble 1, marble 2, marble 3, marble 4, marble 5. Okay, great. And now I want to, and we still have that order doesn't matter. So it doesn't matter which order I choose the marbles. All that matters is the marbles I end up with after the choice has made. So if I choose marble 1, then marble 2, then marble 3, it's the same as choosing marble 3, then marble 2, then marble 1, because I still end up with those 3 marbles after my choice. So order doesn't matter. That's what this means. Okay, so order doesn't matter, and this time I want to know how many different ways are there to choose. So number of ways to choose any 3 marbles. Any 3 marbles out of the 5. Okay, well, again, we're going to do some calculations just like we did last time. So we have 3 spots to fill this time. We got 3 spots to fill. Okay, and well, how many different ways can we do that? Well, we could take marble 1 first, or marble 2, or marble 3, or marble 4, or marble 5. That gives us a total of 5 different choices for the first spot. Now, no matter which of those 5 different choices we made for the first spot, we've still got 4 different marbles that we can choose for the second spot. And then after we've chosen those 4, chosen one of those 4, we've got a total choice of 3 different marbles for the third spot. So that gives a total of 5 times 4 times 3 different ways to choose 3 marbles in different orders out of 5. 3 marbles in a certain order out of the 5. So because, you know, for each of the 5 marbles you choose on the first one, then there's another 4 marbles that you can choose, and for each of those two marbles, for each of those 5 times 4 different choices of 2 marbles, there are 3 other different marbles to choose the third marble. So that gives a total of 5 times 4 times 3 different choices. However, we're not done yet because, well, just like before, we don't, right now we have marble 1, marble 2, marble 3. Right now that's being treated differently because, marble 1 was one of the 5, and then marble 2 was one of the 4, and then marble 3 was one of the 3. But then, conversely, marble 3 could have been one of the 5, marble 2 could have been one of the 4, and marble 1 could have been one of the 3. So it's counted, it's counted the same, it's counted differently to marble 3, marble 2, marble 1. These are considered 2 different choices. I want them to be the same choice because I've already counted, I still have marble 1, marble 2, marble 3 in my hand, whether I choose them in this order or whether I choose them in this order. Doesn't matter. The result is the same. I've still got those 3 marbles in my hand. So I need to divide by the number of different orderings that I can choose those particular 3 marbles in. Well, 3 marbles, there are 3 factorial different ways to arrange 3 marbles. There are 3 factorial different ways, just like there were 5 factorial different ways to order the 5 marbles at the start on the first whiteboard. If we go back. Yeah, I'm right. 5 factorial different ways to order the 5 marbles, and in general, n factorial different ways to order and arrange n objects. So there are 3 factorial, I'll use blue. There are 3 factorial different ways to order those 3 marbles that we've chosen, and hence each choice is being counted 3 factorial different times. We only want it to be counted 1 time. So we got to divide all those choices by 3 factorial. Okay, well, just by observation, 5 times 4 times 3 is equal to 5 times 4 times 3 times 2 times 1 divided by, and we still have 3 factorial on the bottom. That hasn't changed. But we want to cancel out this 2 and this 1. We don't want them, so we better divide by 2 factorial, and 2 factorial is the same as 5 minus 3 factorial. So what we do indeed have is 5 factorial, because 5 factorial is on top, divided by 3 factorial times 5 minus 3 factorial. And of course, this thing here, just as before, we have a special name for it. It's the number of ways to choose any 3 objects out of 5, and that is written as 5 choose 3. And of course, oops, got a text. And of course, 5 choose 3. Yeah, so that's equal to the number of different ways to choose 3 objects out of 5, and most importantly, order doesn't matter. Order doesn't matter. That is why we divided by 3 factorial, because if order doesn't matter, we've got, when we do this calculation, each choice is counted 3 factorial different times because there are 3 factorial, different ways, different orders to choose marble 1, marble 2, and marble 3, for example. Okay. So that's 5 choose 3. It's equal to 5 factorial divided by 3 factorial times 5 minus 3 factorial. And hey, maybe you've noticed a pattern here. I sure did. Well, actually, I had the pattern explained to me. I don't know whether you noticed it or not. 5 choose k, where k can be equal to, I guess, 1 less than or equal to k less than or equal to 5. 5 choose k, it turns out, and you can do this in the same way we did the rest. 5 choose k is actually equal to 5 factorial divided by k factorial times 5 minus k factorial. And actually, there's also nothing special about the number 5. There's nothing special about the number 5 at all. So, in fact, in general, what we can say is that for any objects n, so n objects, and we've got 1 less than or equal to k less than or equal to n, then we have that the number of different ways to choose k objects out of those n is equal to n factorial divided by k factorial divided by, well, yeah, still divided by 5 minus k factorial. And this part here is to eliminate the k factorial different orderings of those selections of k objects, because once we've pulled k objects out, there's actually going to be k factorial different ways to order them. So that's why we divide by k factorial, because we don't want to count, we don't want to count object number 1, object number 2, ... all the way up to object number 3. We don't want to count that as any differently to the choice of object number k, and then all the way back down to object number 1. We want to keep those as the same choice. Okay, so that's what this k factorial is all about. On the bottom there, this 5 minus k factorial. Why the heck did I write 5 minus k? Sorry about that. That's n minus k. Silly me. So k factorial we already just discussed. It's about getting rid of the k factorial different arrangements of each choice. We don't want to count those differently. We want to count them all as the same choice. This n minus k factorial, well, basically that's just to get rid of the rest of the n minus k objects once we've pulled out our k on top. Because n factorial, let me do this on a new page. N factorial is equal to n times n minus 1 times ... all the way down to, say, 3 times 2 times 1. Well, suppose we want to pull all the objects out except for 2 of them. So suppose we want to pull all the objects out except for 2 of them. Well, we're going to have n minus 1 all the way down to 3, and so it'll be n times n minus 1 all the way down to times ... times 3 different choices, doing the same kind of thing as what we were doing before. We don't want this times 2 times 1 on top, so we got to divide by n minus 2 factorial, because n minus 2 is obviously the number of objects we're choosing, and n minus 2 is, of course, well, n minus n is 0, and then minus 2 is just 2, so that's 2 factorial. So that 2 factorial will cancel out these guys. So that's what we're doing. That's what we're doing with this n minus k part. We're getting rid of those last k ones off the top there, out of this n factorial on top. Okay, so that's called combinations. Combinations are when order, where am I going to write this here? Order doesn't matter. Order doesn't matter. It doesn't matter if I choose marble 1, marble 2, marble 3, or if I choose marble 3, marble 2, marble 1. All I care about is that I end up with those particular 3 marbles in my hand at the end. That's all I care about. Doesn't matter what order I chosen. Suppose I do care about the order. So, okay, well, if order doesn't matter, if order doesn't matter, gives me n choose k equals n factorial divided by k factorial times n minus k factorial. If order doesn't matter, well, actually, if I say order does matter, all I need to do is just get rid of this k factorial, because the whole purpose of that k factorial, is to eliminate the double ups, because double ups is the wrong word. eliminate the k factorial different arrangements of which they can be chosen in. I want to divide by that because I don't want to count it, because otherwise each choice is going to be counted k factorial many times. So if I want to pay attention to when order does matter, it's actually just n factorial divided by n minus k factorial. And if we go back to the marbles example, I'm sure you all really love the marbles by now. Marble 1, marble 2, marble 3, marble 4, marble 5. If we go back to the marbles example, M1, M2, M3, M4, M5, and I want to choose 3 of these things where this time the order does matter. So I got 3 spaces to fill, and it matters which one is taken first, which one is taken second, which one is taken third. Then really all I do have is actually, so I've got 5 choices to fill the second one, and then I've got 5 choices to fill the first one. Then I got 4 choices to fill the second one once I've already chosen some marble, say marble 3. And then once I've chosen the first 2 marbles, that leaves me with 3 marbles to fill the third one. So that's a total of 5 times 4 times 3 different choices. And this one considers all of the orders, and that's actually 5 factorial divided by 5 minus 3 factorial, because 5 factorial divided by 5 minus 3 factorial is, of course, 5 times 4 times 3 times 2 times 1 divided by 5 minus 3 factorial. That's 2 factorial, so divided by 2 times 1. So that 2 times 1 disappears. And that's that. So we actually write this as, I think, 5p3. So that's a number of different ways to choose 3 objects out of 5. It's a number of different ways to choose 3 objects out of 5 where order does matter. So that's a really important difference. Order does matter. When order does matter, we use that P symbol usually, although maybe there's a different notation in your class. I don't know. I'm sure your teacher will explain what the notation is. I think this one is standard though. Okay, let me write it out in general one time real quick. In general, when you have n objects, choose k of them, and order matters. This is equal to npk, and that's equal to n factorial divided by n minus k factorial. So n factorial divided by n minus k factorial. And if you want to write it, well, that's the easiest way to write it. Okay, I hope this was helpful. Thanks very much for watching, and see you next time. Take care. Bye.